Okay, for the day 4 lesson, we're going to be talking about application problems with our exponential equations. And as with all application problems, you can expect that you're not necessarily going to be working in a handy 10 by 10 grid like we do for a lot of other things. Let's just look at something we should have seen before. If we see on the left-hand side an exponential formula, we know it's an exponential equation because it has a variable up in the exponent. With a plus inside the parentheses, this is going to be representing growth situations. With the negative inside the parentheses, this will be representing decay situations. So when things are going up or appreciating, then we know we're going to use a plus in there. Like when you put your money in the bank, ideally the bank is paying you for using your money, so that's growing. Decay, when values are going down or depreciating. You buy a new car, you drive it off the lot, and it begins depreciating. It becomes less and less the older it gets. So that you see the only difference between the two formulas is the plus or the minus. In both formulas, A represents the final amount that you end up with. P represents the principal or the amount that you started with. R represents the rate that you're going to be paid or the rate you're going to have to pay, and that's expressed as a decimal. So if you're given a percentage, you'll want to turn it to a decimal first before you plug it into the formula. And then T is the time period, in this case the number of years. So this rate would be given to you as an annual rate. That time would be given as a number of years. Not always though. Sometimes they don't give you the same time period in the rate and the number of periods. So if that happens, then you would want to change either the rate to match the units of time or change the units of time to match the rate. So you could do that in your head and plug in the proper number. An alternative to that is to look at the formula in this version, where in this version you see that you're just turning everything into years. So the number of compounding periods per year, you would take that rate and you would divide by n. If it's a quarterly rate, you take that rate and divide by 4. What we will have often in this unit that's new is something called continuous compounding. In the 3 previous examples, we talked about compounding that occurs every now and then. Maybe it occurs the end of every quarter, maybe it occurs the end of every year, and that's typically what you get when you invest your money into a bank. However, when things are growing or decaying at a constant rate, they just keep, if you think about your elements and half-lives, they're decaying at a constant rate, then we have a different kind of formula. It's still an exponential formula, and the way that I remember it is with Pert shampoo, P-E to the R-T. You'll see that down here. A still represents our final ending amount. P still represents our beginning amount, but instead of having that base of 1 plus or minus a rate, we have a base of E. E is a constant. It's an irrational constant, and let's grab our Inspire to see what E is. If you hit the pi key, you'll see an E in that top row, and if I hit enter, the calculator will give me a rounded off version of it, 2.718. or so. So that's an irrational number. We're going to use it in this formula whenever the problem talks about continuous compounding. So back down to our slide. And a lot of your problems will either require you to substitute into this formula, or they may give you the formula right off the bat and ask you to work with the formula. And that's not uncommon at all. If they give you a formula, then that's what you're going to go with. You're just going to pick up your calculator, start working with the formula. I say calculator because calculator is going to be important in these problems. Simple, straightforward problem. This first one, we're investing $2,000. It's a rate of 5.5% annual, and we're talking about what happens over the course of 45 years, starting when you're 20 years old and ending when you're 65 years old. So we want to know how much we'll have at 65. We want to know our final amount when we start with $2,000. That's our P. We know that this amount is going up, so we'll add. The rate is 5.5% annual. We're going to turn that into a decimal, 0.055, and we're going to raise that to the number of time units. In this case it's years, and we're talking about 45 years. And so you would pick up your calculator, you would type that into your calculator, and the answer you get, there are no rounding instructions, but the answer you get was somewhere around $22,000. But if you're dealing with money, you don't have to round to any more decimal places than 2 decimal places, because in US dollars we don't have any unit of currency that's smaller than pennies. So I'll leave that calculation up to you with a calculator. Let's take a look at what you're more likely to see dealing with exponential equations in this graph, and that's an application kind of a problem. So in this application problem, how long will it take? Well, right now that tells us we are looking for that value t. We're actually looking for the exponent, which means we better have all the other variables in the equation. If the final amount is equal to p e to the rt, and we don't know what t is, then we better know what r is, we better know what p is. E is a constant, so we know it, and we also have to have the ending amount. So let's see what we have in this problem. We have an ending amount of $3,600. We have a principal of $1,200 beginning amount. E is that constant we'll get from our calculator. The rate is given to us at 7% annual, so I can put a 0.07 up there. And that means T is going to be in years, since R is in years. And I have to solve for T. Now, we haven't actually solved for T yet. We don't know how to do this algebraically. So the only way we're going to be able to do this particular problem and solve it is to be doing it with the calculator. And eventually I'm going to put everything on my calculator on the graph, so let's go to the calculator first. We're going to be putting this function into our calculator, make a new graph page. And when you do, well, you can't put that 3,600 in there, you need a function. So we're going to put the other side of it in there, 1,200. I'm going to bring up that E, hit the pi key, and grab the E. Use your caret key to put 0.07, and you can't put a t there. Calculator doesn't have any t-axes, it only has an x and a y, so we're going to put an x up with that 7. And when I hit the enter key, I see absolutely nothing. And that refers to what I said a little bit earlier in the video. You don't have that nice 10 by 10 grid like you do with solving a quadratic equation with no context. So let's hit menu, zoom, and let's try zoom fit and see if that'll show us what we want. Okay, well there's the curve. Now I can see it. It does look like an exponential. I really don't need quadrant 2. If that x-axis is measuring time, remember we changed that t to x. So if that x-axis is measuring time, we can get rid of anything that represents negative time. And I'll make this a -1 just so you can still see that y-axis on your graph. And I also want to see a little bit below the x-axis, so I'm going to go to menu, window zoom, and I'm going to go to window settings. And instead of making my y minimum, well, that's a number, but that's what zoom fit did for me. I'm going to make that a -1. Hopefully I'll be able to see a little bit. Maybe I'll make it a little bit bigger. Menu. And when I say, oh, maybe, yeah, there's really is a little bit of guesswork going on here in order to get your window settings proper, but that's one of the things that New York State would like you to be able to do, is to use those window settings appropriately. So let me see if I can make that y minimum. I'll make it a, I don't know, -50 or something, see if that works out for me. Okay, now you can actually see the x-axis on there. Okay, well, I'm looking to find out what that value of x is for when y is equal to 3,600, or when the function value is equal to 3,600. So the secret to this problem right here is to place that 3,600 on the graph somewhere. And it's not hard to do. I'm just going to go Control G, get back to my graphing line, and I'm going to type 3,600. It shows a horizontal line. Well, I don't see any horizontal lines. What number is this up here? It's not big enough. So now that's a 2,500. I'm going to go up to 4,000. If I go up to 4,000, now I should see that horizontal line that I made at 3,600. And now it should be becoming obvious to you that you're not seeing enough of the graph yet. You need to go to the right. So that x maximum, whatever it is too small. And yes, we're going fishing for the answer here, and that's what this exercise is all about. I'm going to go to Menu, Window Zoom. I'll go back to my window settings, and right now it looks like I'm going out to 10 years. Let me bounce it out to 20 and see if I can see something better. Well, there we go. This intersection point right here, will be the number t, whatever that is, x or t, think of it either way, and this y value will be 3600. So I'm looking for the intersection of that curve and that y value of 3600. So we'll grab menu again, we'll analyze our graph, we need an intersection, you get that dotted line, it's asking you for lower bound, you click, drag past that intersection point and click again, and it will label. If you don't see things, you'll need to use that grabby hand. You can control click to get the grabby hand and move the labels out of your way so you can actually read them. And so now what I'm seeing here is 15.6945, well, and comma 3600. Well, I knew it was going to be on 3600 because that's what I was asking for, but now it gave me the x value. Well, remember the x-axis and the t-axis are the same thing. It's time. So the answer to this problem, and I'm going to have to demonstrate all this on paper, the answer is, to the nearest hundredth, time is going to be equal to 15.69 years. So I know my answer from the graph, and really that's the only way I was able to get my answer, is by finding that intersection point on the graph. So while I'm looking at the calculator page here, I can start down at 0, and if I'm going to go up to 4,000, and you'll have to choose that scale for yourself. Let's see, 2, 4, I'll go 1,000, 2, 4, 2,000, 2, 4, 3,000, and 2, 4. So there's 4,000. I know I'm going to put that horizontal line at 3600 on my graph. I'm also going to need some points to accurately represent this curve. Well, I don't need lots and lots of points. I need enough so that I can make a reasonable curve in between some accurately plotted points. Let me go to Control T for the table. And I know I'm going from 0 to 15 years, so I'm looking for some points I can plot in between, and I don't need a lot of them. Let me go to 5 years. Let me go to 0. I'll start there and see where it actually starts on the x-axis. Okay, so I'm at 0, and I should be at 1200. I'm going to start making a table. So for 0 years, we're at 1,200. That should be no surprise because we started off with $1,200. There's that number right there. Let me go to 5 years here and see what's down there. Okay, at 5 years, looks like I'm at 1703. And rounding is okay. You're not going to be able to get that precise on your graph anyway. Let's go down to 10 years and see what's there. Okay, at 10 years, I've got 2416. And we'll go to 15 years. We know that's going to be really close to our 3600. Okay, I've got 3429. When I say really close, you'll see what I mean when we start looking at the graph. Okay, I'm ready to start plotting those points now. And I'm going to mark this my T, X or T, and this is my A. So let's go to 0, 1200. It's going to be 1250. So there's 1200 about there. Going to 5. Oh, wait a minute. I don't have any labels on this axis, and I certainly need labels on this axis. Well, I know my answer is 15 years, so I think we'll go 1, 2, 3, 4, 5. See if I can fit 20. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 5, 10, 15, 20, and I want to put labels down here. I have context, so I'm going to say time in years. At 5 years, I'm at 1703. So there's 1750, 1703. At 10 years, I'm at 2416. So 2000, this would be 2524. We'll say it's about there. And at 15 years, I'm at 3429. Let's see, 3,429, about there. And let's put our line on the graph. Our line on the graph, our horizontal line, should be at 3,600. So here's 3,500. Let's say 3,600 is right about there. I'll label it to let the whole world know that f of x equals, or a equals 3,600. I'm going to pick up my blue pen and I'm going to draw that curve. And again, it should look like a curve. And now the important point on this graph is right here. This is actually the solution. So I'm going to label, I'm going to identify that point. It's 15.69 comma 3600, and that is actually answers my graphs. So there, what you're going to see, you see everything except the label on this graph, which I'm going to put on right now. A is equal to 1200 e to the 0.07t is that function that we're graphing, and there's our solution right there. So yeah, we're going to have to poke around the calculator. We're going to have to mess around with those window settings until we can find what we're looking for. You can start off by putting the function in and hitting zoom fit, and that may help you find the curve, but you still may need to play around with those window settings in order to get something that shows you that intersection point that you need. Another problem, then this one won't be a graph. This is just a straightforward application of that continuous growth or decay. Well, we're talking about a decay constant of radium, so we're going to be using that PE to the RT formula. A is equal to PE to the RT. Let's see what it's asking and what we know. It's asking how much will remain after 20 years. So it's asking for that final amount. We'll leave that as our variable. It says we're beginning with 50 grams. So I'll type that 50 in place of the P. I'm using my E key on my calculator to represent that constant. The rate, it says negative 0.0004. It's already in decimal form for us. It's decay, so that means that it will be a negative rate, 0.0004 per year. So I know that we're talking about years here when I'm talking about my time. And it says I have 20 years, so I can substitute 20 in place of the t. And this will be a matter of picking up your calculator, type in a 50, type in the e, and then use your caret key to type in this multiplication up here, and I'll leave that calculation to you and the rounding. I'll do one more application problem with you if you want to see me find what I need on the graphing calculator here. Talking about surgery and a circulatory system, how much anesthetic we need in the circulatory system to keep the patient knocked out while we're cutting into them. That's always a handy thing for the patient. Okay, the amount of anesthetic present T hours after 80 milligrams is administered, well, there's an initial amount right there, 80 milligrams, is given by this function. Often you will be given a function. If you're given the function, please use the function that you're given. Don't try to change it around. So this problem is really about how long to the nearest minute can the operation last if the patient does not receive additional anesthetic. So it's all about picking up our Inspire and trying to analyze what the Inspire is showing us and working with the Inspire to see what we need to see. Okay, so we'll start with a new graph page. And you'll put in the function that you have. So you'll just type the 80, open the parentheses, it's a 0.727, close the parentheses, use your caret key. Remember, there are no t-axes in your calculator, so we'll use an x in place. And we see a curve out there. It's supposed to be decay because that's what's happening with the anesthetic. It's decaying over time. So let's begin by saying, well, negative time isn't going to matter. Let me change this axis to a -1. I like to see that y-axis there. And I don't know if I'm seeing enough of the curve here. I'm going to go back and read the problem. Okay, at least 50 milligrams of an anesthetic. Well, the amount of the anesthetic is being measured by in this case, t of t. That's replacing your f of x. So it says we have at least 50. We're going to start with 80, and we don't want to drop below 50. So that y-axis, if it's starting on 80 and we don't want to drop it below 50, we're interested in what's happening in between the 80 and the 50. So I think what I'll do is I'll go back to my graph, and let me say I want to see between 0 and 100. I'll put 100 up here. And I don't need to see down to -6. Whoops. As soon as you do that, you lose your number, so you can't type over it. So I can do that through window settings. So let me go to Menu, Window Settings, and I'll make my Y minimum, I'll make it a -2. Okay, now you can see that time axis. Again, use your control click for the grabby hand if you need to move labels out of your way. And we're talking about needing at least 50 milligrams of an anesthetic. So we started with 80. We're interested in where the 50 is. So let me put a horizontal line on the graph. We'll do a Control G, and we'll type 50 to put the horizontal line at 50. And so it looks like if this is our time axis, we start time 0. So as time passes, we're starting with this level, but it's coming down, and here's the danger zone. We don't want to drop below 50. So we want to know what that number is right there. I know the y coordinate's 50, but I don't know the x coordinate. So what do? I hit Menu, Analyze Graph, find the intersection point, click to the left of the intersection, click to the right of the intersection, and it'll label that for us. Now we're talking about, we've got some units change in this problem going along, so I'll talk about that in just a minute. I know that this point, I know the y value is 50, and it looks like the x value, or the t, is 1.47 nearest minute. Let me just hold on just a minute. Okay, well, logic would have me reconsider what is actually being measured on that x-axis. If you start surgery and you don't have enough anesthetic after 1.47 minutes, that's not a good situation. If you go back and you read the problem carefully, it actually talks about T hours. T is in hours, but you have to answer the question in terms of minutes. So this point right here on our calculator screen tells us that anesthetic is going to be okay for the first 1.474 hours. But we're going to have to turn that into minutes. So what do? We multiply 1.474 hours times 60 minutes, and that'll give us our minutes here. Let me get a calculations page. So 1.474 hours times 60 minutes per hour, and that's going to give us 88.44 minutes. And it says how long to the nearest minute, so we can round that off to 88 minutes. Okay, now we're graphing the situation here. We're graphing the situation. We have to go back to our calculator. We'll have to get the table in order to come up with all those values. We're working with T, and it's uppercase T of T, which represents the amount of anesthetic in the blood. We know that at 0 it's at 80. We know that by the time we get to 1.4 it's going to be we're already past what we are concerned about, so I'll just go 0. I suppose you could do a 1 in here, do a 2 in there, and that'll be okay. You'll see a curve going on there if I label that. So let's call this 0, 2, 4, 6, 8, 10. So I'll call that 1 and 2, 4, 6, 8, 10. Now remember, our function is in terms of hours. So I'm going to be writing time in hours down here. And we were interested, on the calculator we said, well, we'll go from 0 to 100. So 2, 4, 5, 2, 4, 5. That's going to be 25. That's going to be 50. 2, 4, 5, 75. And 2, 4, 5. That's 100. Okay, so let's, we know we're starting at 0, 80. That was a given. So I'll plot that there. And I'll have to go back to the calculator to get my table of values. And there are ways to change the settings on the tables. Back at this graph, if I do a Control T, you can do that through the menus if you want, but if you take a look at the points that are plotted here, they should be sufficient to give you a reasonable curve. I've got a 1 and a 58. You don't have to worry so much about the decimals. You can't plot that accurately anyway. And when I'm at 2, I'm at 42. So we can go ahead and we can plot that 0, 80, plot that 1, 58. So 50, 55, right about there. And then 2, 42. So we're up at 45. 42 looks like it's right about there. Okay, we've got decay going on here, so we're going to make a curve. Try not to make it look like a line. Okay, represents decay, and the number that we're interested in is 50, so I put that t of t, or f of x equals 50 on my graph. I'm going to make that same line here. The point I'm interested in is this point right in here. We already determined from our graph that that point was 1.474 comma 50. And so now this, we want to circle that intersection point. I don't think I said that on the last graph, but you do want to circle it. It shows it's a solution. And so all of my work, that answer, the 1.474 that I'm using, comes from the graph. And so you have to have a complete and thorough graph to show that. Let's label this curve. T of t is equal to, take a peek at that, 80 times 0.727 to the t. I want to label this horizontal line, y is equal to 50. I should put a label on my y-axis as well, so we'll call that amount of anesthetic, and that is in milligrams. So we got some units also. So the graph is actually the solution. The only thing I had to do in addition to that in this case, I've got a table, got everything labeled, got my points circled, got my axes labeled, got my scales proper. And the last thing I had to do, because they asked me to change units on here, is change the hours to minutes and round off as requested, nearest minute, 88 minutes, and you're done.